So one thing you need to know about the periodic table is that there's a lot more information present in it than immediately meets the eye. So if you look on this periodic table, you can see that you got hydrogen, it's atomic number 1, this is its mass. So that's the first immediate information that you can see about each element. The second thing that you already know is that the arrangement of it lines up with the electron configurations. So the period number is equal to the energy level of its highest electrons, its valence electrons. The group number tells you its oxidation number and how many valence electrons it has. So you already have some of that information, but there's also trends of the properties of the elements that tend to repeat in the periodic table. So they follow certain trends. In this video, we're going to talk about reactivity. In the next video, we'll talk about atomic radii, and the following one, ionic radii. But before we start everything, I want to, hold on, there we go, it popped up. I want you to write this down, just remember this. A lot of the trends for reactivity, or the reasons behind them, have to do with the fact that metals like to lose electrons, non-metals like to gain electrons. So before I even go into the trends, I want you to know these two things and keep in mind that the trends for metals and non-metals is opposite because they like to do opposite things. Metals like to lose, non-metals like to gain. One quick thing I want to preface here too is, remember we talked about the valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. All elements like to be like the noble gases. They like to have 8 valence electrons. Well, except helium. Helium likes 2. They all like to be like noble gases. So if you're lithium looks like this. It's got 1, 2, 3 electrons. Lithium has to either gain 7 electrons to be like, 7 electrons to be like neon, 7 electrons on this second energy level, or it can just lose 1, and now all of a sudden this second energy level is gone because there's no electron on it, and it has 2 valence electrons, which makes it look like helium. So that's why lithium likes to lose an electron and become a +1 charge. Same thing magnesium. It can either gain 6 electrons to be like argon, or it can lose 2 to be like neon. It's easier to lose 2 than it is to gain 6, so magnesium almost always loses 2, or it always loses 2 electrons, and it forms a +2 charge. Now if we look over at the non-metals over here, fluorine has 7. It can either lose all 7 to be like helium, all 7 of its valence electrons, or it gains 1 to be like neon. Well, it's going to always gain 1 and form a -1 charge. Same thing, oxygen. It'll almost always gain 2 electrons because that's easier than losing 6 of them. So just keep that in mind as we move forward here. Okay, so the reactivity trends of groups. Now for the metals, as you go up and down in a group, so a group is a column, so this right here would be a column. Hydrogen is not a metal, so we're just looking at lithium, sodium, potassium, rubidium for this group. The reactivity increases going down. So as we go down, they get more and more reactive. They're more likely to react with things. Now, why do they do that? Because the electron is farther away from the nucleus. As they get bigger, the elements get bigger. The electron that francium is letting go of is a lot further from the nucleus than the electron that lithium is letting go of. So I have a picture over here. Lithium's electron is pretty close to the nucleus in the middle here. So it's held on pretty tight because we've got a negative electron and a positive nucleus. The closer the opposite charges are, the stronger the attractive forces is felt. This distance is a lot further, so the positive charge here has a looser grip on that electron. So potassium's electron is easier to let go than lithium. Think of it this way. You all know magnets, right? The closer together they are, the stronger the pull. It's the same thing here. These are closer together, so it's a stronger pull. These are further apart, it's a weaker pull. So if we move the magnets apart, the force pulling them together gets weaker. That's why it's easier for potassium to lose. So as size gets bigger, it's easier for metals to lose their electrons. They become more reactive. Okay, the reactivity trends of nonmetals. The nonmetals get they get more reactive as you go up. So if we're looking at this column, the halogens, fluorine is the most reactive element in this group because they get more reactive going up. And it's the same reason the metals get more reactive going down. But because they do opposite things, the trend is opposite, right? As I go down, they get bigger. There's more shells, bigger atoms. The electron is further away. It's easier to lose it. The opposite's true. As I go up, they get smaller. They get better at gaining electrons. The smaller you are, the easier it is for your nucleus to pull in and grab a negative electron. So smaller size, you get more pull with the nucleus. Smaller nonmetals are better at picking up electrons. So again, fluorine's positive center is doesn't have to pull an electron in quite from as far away. Whereas bromine, look at all these shells. This electron is a lot further away. It is harder for that nucleus to grab a hold of it. Whereas fluorine is really good at pulling in electrons because it doesn't have as far to pull that electron into. So nonmetals, remember, they like to gain electrons. Smaller elements are better at sucking in electrons. Okay, the reactivity trends of rows. Notice I left the column trend in here, but we're going to add the rows. So going left to right, the metals get more reactive as you go left. Why? Because the farther from the octet you are, the more you want to lose electrons. Or actually, I like to phrase it a different way. I like to say, okay, all of these elements have one valence electron. These have two valence electrons. Is it easier to lose one electron or is it easier to lose two electrons? The answer is it's easier to lose one electron. If you lose that one electron, you become like a noble gas. So these elements, these metals, remember hydrogen doesn't count, these metals are more reactive than these metals because they only have one to lose. These have two to lose. So they get more reactive going to the left. And now if I go over here, these metals have three valence electrons. They're even less reactive. So more reactive going that way. So what this means is if my elements or my metals specifically get more reactive going this way and down, that leads francium as the most reactive metal. So what I have here, just showing you an example, lithium has one electron, valence electron, beryllium has two. It is easier to lose one than it is to try to lose two valence electrons. It's easier to lose two than three and three than four. Technically, carbon isn't a metal, so it shouldn't even be there. But I'm just showing you as you go across, it goes 1, 2, 3, 4 valence electrons. As you move to the left, easier to lose less. Okay, nonmetals, it's the opposite, just because they do the opposite thing, right? Nonmetals, the reactivity increases to the right. Why? Hold on, I'll get to that in a second. Why? Because the closer you are to the octet, the more you want to gain electrons. Fluorine is 1 away from being like neon. Oxygen is 2 away from being like neon. Fluorine is way more desperate to pick up that 1 electron, and it's easier to pick up 1 electron than it is to pick up 2 electrons. So that's why they get more reactive going this way, because they're getting closer to the octet. So that leads us to if the elements or the nonmetals get more reactive going to the right and they get more reactive going up, that leads fluorine as the most reactive element. We do not include noble gases because they're notoriously unreactive. They're the only elements that don't react. So when it comes to reactivity trends, you ignore the noble gases. So if I ask you which element is more reactive, bromine or krypton, it's always going to be bromine. It's never going to be the noble gas because they are the least reactive elements on the periodic table. They do kind of violate this trend because yes, technically they are on the far right, but they aren't reactive at all. So the halogens are actually the most reactive nonmetals. So here's the example again. Fluorine has 7 valence electrons. It only has to pick up 1, whereas oxygen needs to pick up 1 here and here. It needs to fill both those spots. It's easier for fluorine to fill its 1 valence electron than oxygen is to fill 2. Same thing, nitrogen has to pick up 3 valence electrons, which is even harder. So they get more reactive going that way. So we'll do a little bit of practice here. Which one is more reactive? Now the first thing you have to do is identify, are you dealing with metals or are you dealing with non-metals? Because that makes a big difference on which way you're looking. So the first two, sodium and aluminum. Sodium is here, aluminum is here. Now, are these metals or non-metals is the first question. And remember, we've got the stair-step line. We'll add that here real quick. Your stair-step line, non-metals, metals. So they're definitely on the metals side of the stair-step line, so we follow this pattern. Sodium is further this way, so it is more reactive. They get more reactive going to the left. So I'd say sodium is the more reactive. I'm going to erase all that. Sodium. Now, nitrogen and neon. Nitrogen, neon. You might be like, okay, we're going this way to the right. That would, and they're nonmetals, so neon would be more reactive. But don't forget, neon is a noble gas. Noble gases will never be the more reactive element. So nitrogen is definitely more reactive because neon never reacts. We've got chlorine and bromine. So chlorine, bromine, they're right on top of each other. So more reactive going up, that would make chlorine more reactive. Then we got titanium and calcium. Titanium, calcium, they are metals. So the first thing you got to do is identify that they're metals. Calcium is more reactive because it is to the left. Metals are more reactive to the left. Now, you are not allowed to write these trends on your periodic table. I would like you to memorize them. So make sure you're memorizing them as you practice them here. We've got nitrogen and arsenic. Nitrogen, arsenic, nitrogen's higher. That is it. You should do the last 3. Let's pause and do the last 3 on your own. Okay, hopefully pause and you got them done. We've got manganese and iron. I'm going to go quick here. Manganese is further to the left. Calcium and germanium is over here. Calcium is further left. And then we've got bromine and argon. Bromine and argon. Argon is a noble gas. It's definitely not argon, so it would have to be bromine. Okay, so that last example, sorry I got cut off there. Argon is a noble gas, so that means bromine's more reactive, right? Noble gases are automatically less reactive than any other element you're comparing them to. Unless it's another noble gas, then cross them both out because neither of them react. One last thing I want to point out, because a lot of students have questions about this. If I give you an example of these two elements right here, it's obvious that this one is more reactive because it's further to the left and it's further down, and they're both metals. But a lot of students ask, well, what if you gave me an example like this? Sorry, let's actually erase this. What if you gave me an example like this? Calcium and sodium. We'd say, well, sodium is further to the left, but calcium is further down. I wouldn't give you an example like that because I wouldn't expect you to know that. So don't worry about, oh my gosh, what do I do if one's further to the left but the other one's further down? They'll be obvious. Like these examples, one was either, left or right, or up or straight up and down, right? Or, like I said, if I gave you something like this and like this, well, zirconium is further left and further down. So I wouldn't give you questions that have an ambiguous answer. They're going to be very clear cut. The only time I would maybe give you an example like that would be like chlorine. Let's see here, and I guess that doesn't really work either way with a noble gas, but that's fine. And you'd only ever compare nonmetals to nonmetals and metals to metals. If I ask you to compare a metalloid in there, just treat it as if it's the same as the other element you are working with. So there you go. That is where we will end this video.